The alert said latency. P95 response time had jumped from 120 milliseconds to over 3 seconds. Requests were still succeeding. Error rate was low. But everything felt slow. Slack messages started coming in. Search is taking forever. Checkout is lagging. Pages are loading but really slowly. So we opened the dashboards. CPU looked fine. Across the cluster, it hovered around 35%. Memory usage was stable. No pod restarts. From the infrastructure perspective, nothing was under pressure. Yet the system was clearly slowing down. Environment context. Our platform ran on AWS. The back-end services lived in a Kubernetes cluster on EKS. About 160 pods handled traffic across search, recommendations, checkout, and user profiles. Traffic averaged around 6,000 requests per second during peak hours. The architecture was microservices-based. Requests flowed through an API gateway into multiple downstream services. The search service was one of the most critical components. It queried a distributed search engine cluster running on dedicated EC2 instances. The search cluster indexed product data and returned results used across the platform. The database layer used PostgreSQL on RDS for transactional data. Redis handled caching for frequently accessed queries. CI pipelines ran through GitHub Actions, and deployments were managed using Argo CD. Monitoring included Prometheus, Grafana, and Datadog. Normally, when latency increased, CPU or memory usage would spike as well. But this time, those signals remained calm. Initial symptoms. User complaints were consistent. Search queries returned results, but they took several seconds instead of milliseconds. Checkout pages waited on search results before rendering recommendations. That delay cascaded into multiple parts of the user experience. Metrics showed that request throughput remained stable. The system was still handling traffic. It was just doing it slowly. We checked the API gateway. No signs of throttling. Load balancer metrics looked normal. Then we looked at the search service latency. It had increased significantly, but the CPU usage on the search nodes was still low. That was the contradiction. High latency with low CPU. Something was wrong, but not in the way we expected. Investigation and escalation. The first hypothesis was a network issue. Perhaps requests to the search cluster were delayed due to network congestion. We checked network throughput and packet loss. Everything looked normal. Next, we suspected the database. Search queries sometimes relied on metadata from Postgres, but database query times were stable. Then we examined the search cluster more closely. Disk usage looked fine. Memory usage was steady, but one metric stood out. Disk I/O wait time had increased. Not dramatically, but enough to be noticeable. We looked deeper. The search nodes were performing frequent disk reads, much more than usual. That suggested the system was not serving queries from memory. It was hitting disk more often. Root cause. The root cause was a subtle change in cache behavior. Earlier that day, a configuration update reduced the memory allocation for the search engine's query cache. The intention was to free memory for indexing operations, but that change had an unintended side effect. With less memory available, the search engine evicted cached query results more aggressively. Instead of serving queries from memory, it had to read data from disk. Disk access was significantly slower than memory access. Even though CPU usage remained low, each query took longer to complete. Because the system was not CPU-bound, traditional metrics did not show stress, but latency increased across all search requests. That latency propagated through the entire application stack. Mitigation and recovery. The immediate fix was restoring the original cache configuration. We increased the memory allocation for the query cache and restarted the affected nodes. Within minutes, the cache began warming up. Frequently requested queries were served from memory again. Latency dropped steadily, from 3 seconds to 1 second, then back to under 200 milliseconds. User reports stopped shortly afterward. The system returned to normal performance without any increase in CPU usage. Total incident duration lasted around 40 minutes. Post-mortem reflection. What actually failed was our assumption. That CPU usage is the primary indicator of system health. The system was not CPU-bound. It was I/O-bound. Because the monitoring focused heavily on CPU and memory, we missed the early signs of degradation. The cache configuration change had been reviewed for resource efficiency, but not for performance impact. Observability gaps made it harder to detect the real issue quickly. Engineering lessons. Latency issues can originate from disk and network bottlenecks, even when CPU appears healthy. Cache configuration changes should be evaluated for their impact on performance, not just resource usage. Monitoring should include I/O metrics and cache hit rates alongside CPU and memory. Systems that rely on caching must treat cache behavior as a critical performance component. Most importantly, a system can appear idle while still being slow if it spends its time waiting. That incident reminded us that sometimes the system is not working harder, it is simply waiting longer.